Alright guys, welcome to Crown Smart. In this video we want to do more on topology. So let x equal to the set of natural numbers. Okay, let x equal to the set of natural numbers, and let tau be the empty and kn, where my kn is defined as n plus 1, n plus 2, and so on, where n is coming from the set of the natural number. Okay, now we want to show that this is a topology on what? An x. Remember, my x is the set of natural number. Now we want to show that this is a topology on what? On n. Now let's start like this. Okay, before we show that it's a topology, let us do something first. Now let's understand what kn is. Now kn, let's say if we have k1, now remember n is coming from the set of natural numbers, so this is an element in the set of natural numbers. So if I do k1, this will be 1 plus 1, which is 2, 1 plus 2, which is 3, 1 plus 3, which is 4, 5, 6, and so on, right? If I do k2, I will have, this time around, remember it is starting with n plus 1, so it's going to be 2 plus 1, okay, 2 plus 1, which is 3, 3 plus 1, which is 4, 4 plus 1, which is 5, and so on. Okay, so if I do k3, this is going to be 3 plus 1, which is 4, 3 plus 2, which is 5, 6, and so on. Okay, now let's say we pick a point. Let's say we pick a point, n naught. Now observe, n in n here varies. N could be any number, but when we are saying n naught, we mean a point in what? In this set of natural number, just a point. Now if I pick a point in n, therefore this becomes kn naught becomes n naught. Okay, replace every n here with what? N naught. Okay, n naught plus 1, n naught plus 2, n naught plus what? 3, and so on. Okay, so if I pick another point, n alpha, in the set of natural number, this is just a point, then this becomes kn alpha. This becomes n alpha plus 1, n alpha plus 2, n alpha plus what? 3, and so on. Okay, now reason I'm introducing this n naught and n alpha is because I want to use it. Okay, but just take it that this could be any point. This could be a point. This is a point. This is also a point. Okay, a point they are fixed value. Okay, so I could call my n naught to be 5. I could say it is 6. Any value that is fixed. While n here varies. N could be any of the numbers. Now let's show that this is a topology. We want to show that tau here, which is the empty, and kn is a topology on the set of natural numbers. Now observe that I said that k1 is this, k2 is this, k3 is this. You also have k4, k5, k6. Now another thing you need to observe is that this topology is totally ordered. This topology is totally ordered. What do I mean it's totally ordered? It's ordered in the sense that, let's say you have empty, you have k1, k2, k3, k4, k5, and so on to certain kn. Observe that empty is a subset of kn, kn is a subset of whatever thing we have there, and whatever thing we have there is a subset of k5, k5 is a subset of k4, k4 is a subset of k3, k3 is a subset of k2, and k2 is a subset of k1. Okay, so since this can be expressed as this, it shows that this topology is what? Is well ordered. Okay, I mean it's totally ordered. Now, if you look at it very well, you see that K3 is a subset of K2. K2 is a subset of what? K1. Okay? Now, reason I'm mentioning all this is because I want to use this to what? To do the proof. Now, I want to show that that is a topology on N. Now, the first thing I need to show, remember, if you want to show that a set, we want to show that this tau is a topology on a certain given arbitrary set X, we have to show that it satisfies three conditions. Now, we have to show that the empty set is in tau. Now, of course, the empty set is in what? Tau by what? By definition. Now, look, the empty set is already in what? In tau, which is there. Now, secondly, or you can say it is trivial to see that the empty set is in what? In tau. You can actually say that it is trivial to see that the empty set is in what? Tau. Now, the whole set is in tau. Since K1 is equal to what? The set of natural numbers. Now, observe that the set of natural numbers is actually K1. Set of natural number is the set containing 1, 2, 3, 4, 5, and so on. So K1 is actually this because it is defined as this. So this becomes the set of what? Natural number. So we have shown that the empty set is there, the whole set is there. Now we need to show that the arbitrary union of set in the topology is in the topology. Okay, we need to show that the arbitrary union of set in the topology is in the what? Topology. Now, before we do this, observe that if I do Kn union empty sets, observe that I still have what? Kn. And Kn could be K1, it could be K2, it could be K3, it could be K4, it could be K5, it could be K6, right? So I will only focus on the Kn. I will ignore the empty. Okay, so I'll only focus on what? Kn, to see if the arbitrary unions of all these Kn will it be in the topology, because I know that if I do take any of the Kn union the empty set, I will still have one of those Kn inside the empty set. If I do K1 union empty, it is K1. If I do K2 union empty, it is K2. So it is a trivial case. So let me focus on the union of the what? Of the Kn. Now, remember, I want to show that the arbitrary union is in the what? Topology. So what I will do is, I will say, take any class Kn where n is coming from set of natural numbers. Okay, where n is coming from the set of natural numbers. Then remember, this is a class Kn. Sorry. Take any class Kn which is a subset of what? Tau. Okay. Then since this what they call it, since this is well ordered, since my Kn is well ordered, then since my Kn is totally ordered, this implies, since my Kn is totally ordered, okay, remember, what do I mean by totally ordered? You can have let's assume we have K1, K2, K3, K4, K5, K6. You have that K6 is a subset of K5, K5 is a subset of K4, K4 is a subset of what? K3, K3 is a subset of K2, and K2 is a subset of what? K1. Okay, now that is what it means by being totally ordered. Now, since my Kn is totally ordered, this implies that there exists an n naught, okay, which is the smallest. There exists some n naught in n. There exists some n naught in n, which is the smallest number, which is the smallest number in what? In n. So there exists an n naught in n, which is the smallest number in n, such that such that the union of Kn n in n is equal to n naught, okay, n naught plus 1, n naught plus 2, n naught plus 3, and so on. And of course, whenever we have this to be like this, then this is simply Kn what? N naught. Now what does this thing mean? This means that there exists an n naught in n, which is the smallest number in n. Now if you do, look at this now, look at this very carefully now. Let's assume I'm doing the union of K1, K2, K3. Now if you do the union of K1, K2, K3, what do you have? The union of this will simply be K1. Now observe that 1 is the smallest number, because we have 1, 2, 3. 1 is the smallest number, right? So if 1 is the smallest number, then this set can be written as 1 plus 1, 1 plus 2, 1 plus 3, 1 plus 4, 1 plus 5. Okay, now let's now focus on this 2. If I do K2 union K3, observe that the union will fall on the smallest number 2. So this K2 can be written as 2 plus 1, 2 plus 2, 2 plus 3, of course 2 plus 3 is 5, 2 plus 4, and so on. So that's what just happened here now. So I say there exists n naught in n, which is the smallest number in what? In n, such that this union can be written as this. And since this union can be written as that smallest number, this union of this can be written as this smallest number, then observe that if whenever we write something like this, this is what? Kn naught. Remember I said if we have Kn naught, it can be written as this. Okay, now but Kn naught is a subset of what? No. But the singleton, but this is a subset of Kn, where n is in n. Okay, but this is a subset of this. Okay, so since this is a subset of this implies that Kn naught is in what? Is in tau. Remember, this is a subset of this, and this is a subset of this. Okay, so if this is a subset of this, and this from the question is a subset of tau, this implies that Kn naught is in what? Is in tau. Okay, now we have shown that means this implies that the arbitrary union, remember the union of this is equal to this already. Okay, let me write here, let me put here that the union n in n of Kn is equal to Kn naught. Okay, now so this implies that the union of Kn n in n is in what? Is in tau. So we have shown that the arbitrary union is in what? Is in tau. Next, we want to show that a finite intersection is in what? Is in tau. We want to show that the finite intersection is in what? Is in tau. Now, before we continue, I need you to observe something. Before we continue, I need you to observe something here. I need you to observe something. Now observe that if I do Kn intersect the empty set, this gives me what? Empty. Okay, so any of the Kn intersect empty sets will give me what? Empty. So if I do K1 intersect empty set, I have empty. If I do K2 intersect empty set, I have empty. If I do K3 intersect empty set, I have what? Empty. So that becomes what? Trivial. So our focus is to show that intersection of Kn, okay, a finite intersection of Kn, n equal to 1 to a certain m. Okay, is in what? Is in tau. Okay, now reason why I ignored the empty set here is because if I do any of the kn intercept empty set, I still get empty, and empty is in the what? It's in the topology. Okay, so my focus now is to do the intersection of only the kn, focus on only the kn, and see if this kn, if I do their finite intersection, will it be in the topology. Now observe that if I use, of course, finite intersection has to be like this, right? Now observe that if I use if I take n equal to 1 to m, then I'm being biased here, because here I'm working from 1 to a certain m, whereas I could have a case where I could have k2, k3, and k4. Now if I do this intersection is a finite intersection. Okay, so now here of course I'm starting from 1, so I'm going to be what? Biased. Okay, because from here it's saying that it must start from 1. Here you have k1, intersect k2, intersect k3 to a certain m. But here I want it to be k2. Okay, here I might have a case where I have k2, k3, k4. Okay, I might have a case where I have k2, k3, k4, or I might have a case where I have k100 intersect k150. This is a finite intersection. So now there's how to do this. Okay, there is how to do this. Now what we are going to do now, watch what I'm going to do now. I'm going to say let I be a subset of n be a finite set. Okay, remember n is the whole set, right? So let I be a subset of n be a finite set. Now if I a subset of n be a finite set, what does this imply? Then this implies that let I be a subset of n be a finite set. Then take any collection kn where n is coming from what? I, be a subset of tau. Okay, take any collection. Remember, this collection will now be a finite collection. I here is the index set, is a subset of n. So therefore it means that the collection will be what? Will be finite, because if the index set is finite, then the collection will be what? Finite. So take any collection which is a finite collection, okay, which is a subset of tau. Then since kn is totally ordered, please forgive my handwriting. Since kn is totally ordered, okay, this implies there exists an n alpha, okay, in I. There exists an n alpha in what? In I. Okay, so I is a subset of n, and it is what? A finite set. Actually, it's a finite set. Okay, so if this is if I, let's say, it's an assumption, I could be 5, 6, 7, 11. I could be this, and this is actually a subset of what? The set of natural number. Observe that I is finite. Okay, so I could have k5, k6, k7, k11. So my kn in this case could be k5, k6, sorry, not like this. So this collection kn will be k5, k6, k7, k11. Okay, this is just an example. So I could be any, that's why I say let I be a finite set. Then take any collection to be a subset of this. Okay, this is just an example to show you, to explain what I'm doing here. Now, since Kn is totally ordered, that means you can have, since you have K5, K6, K7, K11, we know that K11 is a subset of K7, K11 is a subset of K7, K7 is a subset of K6, and K6 is a subset of K5. So since Kn is totally ordered, then there exists an N alpha in I. There exists an N alpha in I, which is the largest number in I, such that, which is the largest number in I, such that the intersection n in I over the Kn, no, the intersection of Kn, where n is coming from I, can be written as n alpha plus 1, n alpha plus 2, n alpha plus 3, and so on. And of course, this will give us what? Kn alpha. Okay, we are saying that that there exists an n alpha in I, which is the largest number in I, such that their finite intersection, this intersection, remember this intersection is finite because n is coming from a finite index set. So this intersection can be written as n alpha plus 1, n alpha plus 2, n alpha plus 3. Okay, and of course this is equal to what? Kn alpha. Okay, so since this can be written as this, now let me give you an example of what I'm trying to say. So if I have K1, K2, K3, okay, of course, now if I do the intersection will be the smallest one. Okay, of course, this intersect this will give me this. This result intersect this will give me what? Will give me this. Or the intersection of this, this, and this will give me what? This smaller one. Now observe that if the intersection is this set, what is the value? The 3 is an element in the set of natural number, right? So 3 is bigger than 2 and 1, right? So 3 is the largest. And this set can be written as 3, 3 plus 1, 3 plus 2, 3 plus 3. Okay? So this set can be written as 3, 3 plus 1, 3 plus 2, 3 plus 3. Now if I have these two, if I consider these two sets, K2 and K3, if I do their intersection, I have K3, right? So you see that the largest number can be written as 3, 3 plus 1, 3 plus 2, 3 plus 3. If I consider K1, K2, that is the final intersection of K1, K2, observe that the largest number is what? 2. It falls with the largest number 2. So I have 2, 2 plus 1, 2 plus 2, 2 plus 3. Okay, so that's just an example. That's just a way of explaining what I'm doing here. Now we have this, remember, the n alpha in I, such that, okay, which is the largest number in I, such that their intersection will give me this, can be written as this. Now since this is written as this, then this becomes what? Kn alpha. Okay, remember where I said that if I have Kn alpha, it can be written as what? As this. Okay, now since it has Kn alpha, what does this mean? Now observe that, but Kn alpha, this singleton, is a subset of this collection n in I. Okay, so observe that this is a subset of this, and this is a subset of tau. So this implies that Kn alpha is in what? Tau. Also remember, please, I keep forgetting this, since this is equal to this and this is equal to this, then this implies that this intersection Kn n in I is equal to what? Kn what? Alpha. So if Kn alpha is in tau, what does this imply? Then this implies that the intersection of Kn n in I is in what? Is in tau. So we have shown that the empty set is in tau, the whole set is in tau, the arbitrary union is in tau, and the finite intersection is in what? Tau. Then we can now conclude that tau is a topology on what? On n. Remember that when we have n comma tau, this becomes what? A topological space. So this is a what? A topological space. Okay, so thank you very much for watching this video. I hope you understand it. Please don't forget to like and subscribe. Thank you.